Hello, if you can hear me. Hey guys, and welcome. Wow, I'm a little bright right now. Try and turn down my color here. Hello. Am I changing? There we go. There's a little better. Hello, and welcome back to my lab. This is another stream. I'm going to be using the Analog Discovery 2 once again, just playing with some simple RC stuff tonight. I've been doing this mostly to try it out and to keep fresh on my basics. Who doesn't need to get a little bit better at the basics of electronics? I know I always do. What I'm hoping to eventually do, and this is also acting as my mouse pad, which is a little bit blasphemous, but is to get into this, and not even this actually, and the other one's really stacked up with stuff, but there's a workbook, and that's what I'm really hoping to get to eventually, is to be going through the workbook, brushing up on a lot of that stuff. That's where a lot of the basic transistor stuff comes from, or at least, I was just simply doing NPN stuff. I'm going to start following along with that and just really just going through it, kind of like a study recitation session. People that have watched before, and hello everyone welcome back everyone who has done this before. If you watched this before, you probably know that I've made mistakes. Woohoo. And yeah, that sucks. But it's just going to happen because I'm kind of, how to explain this? A lot of the knowledge is there, but there's a lot of other stuff going on up here, you know what I mean? And I guess that's where it comes from, is that, sometimes you just kind of forget the basics, and that's why I'm doing this whole refresh in the first place. That's enough about me. So let's take a look at what we're going to be doing here today. I'm going to, well, first off, I want to show you, as I have been mentioning, there is a forum. So this is where I've been posting the past streams and stuff like that. You can see I'm also posting them on Twitter and stuff like that. But I would love people to participate here. Doesn't seem like anyone has since I've recommended it. But, if you got any questions, you want me to stream about anything in particular, just let me know. This is a good place to do it. Forum.contextualelectronics.com. This is all free and open to the public. It looks like there is someone new here. So, Arnold. Welcome, Arnold D. I'll have to check that out later. Anyways, this is also how I normally record stuff for Contextual Electronics. It's just that I've wanted to do this basic stuff before I get back into the project stuff. So, without further ado, let's take a look at the setup that I've been working with. Here, I added a couple more screens. So you see on the bottom right there, that is the camera that broke last time, but that is my kind of overhead camera, and then this is my up close camera, and then I also have the two generators on the left, the two signal generators on the left, and then I have the two scope channels rather on the right. You can see these are actually old waveforms. Neither of these are running. If I hit run here, you're going to see it flatten out basically as it resamples. Okay, so what you can also see is that I simply put this. I just put an RC circuit together, really simple. It's a 10K and a 0.1 microfarad capacitor, and I'm just going to use it as a platform for, first thing I'm going to show is another thing that we're going to be using in the course, hopefully, in the near future here, is this BNC breakout board. And you see that it does exist, and there are two cameras here kind of looking at the same thing, so hopefully it's not too disorienting. But this actually plugs into the Analog Discovery 2, and you can see this. It does have the markings on here, and what you can see on this one, which I noticed the other day, is that the similar markings for the scope channels and everything else, it says NC, which is no connect. And so you're really not supposed to hook up. So basically, and you can kind of see it in the layout as well. You can't really see it. In this one? No. Wonder if let's try this. Maybe this will work. If I turn on my, does that work? Yeah, you can kind of see it there. So you can see it's definitely segregated, right? So the scopes channels are on the left side here. Those are all segregated, and then it looks like it draws off. You can't really see it, but it draws off the waveform on the top side here, and it just sends it over to the right side. Those are the two waveforms, and it's just a BNC connector. So that's how we're doing all this stuff. So what I'm going to do is just plug this in, and then I'm going to actually simply use, well, I'm going to use, well, how many channels do I have even? I guess I have upwards of 3 channels. But what I'm going to do is have one as a waveform, and I am going to use a BNC, or sorry, a scope probe here. But what I'm going to do is set it to 1x. So set it to 1x here. Oops, 1x instead of 10x. Right, put the witch's hat on here. That's what we call this thing. If you've never seen one before, it's just a little clippy. Oh, that's the wrong one though. Yeah. So what I also did is, what I also have rather, is a this is a 100x probe. So these are 10x, 1x and 10x, right? The normal ones that come with the Analog Discovery 2. And then I went out and I bought a 100x probe, which means I can go up to 2 kilovolt input, which seems a little high. Actually, that is high. It's not actually 2 kilovolt input, because this thing can only, I don't think it can do a standard scope input can do. Most scopes can do, you know, a couple hundred volts in input here with a 10x probe. I guess that would be 10x probe on 200 volts would be a 20 volt input, right? Yeah. So then, yeah, I guess this could do 2,000 volts at a divided by 100 would be 20 volts input. So what it really is it's just doing a divider in here, and then there's capacitance as well, which is meant to be controlled, and you can, you know, turn the little screwdriver thingy here. I don't know if this is, yeah, so this one's actually not switchable. So we might use this as backup, but I'd have to change the settings or something. Well, anyways, let's also plug in another one here. So this one I am going to set to 10x. So I'm going to plug in this to channel 1. Okay. And what you may or may not be able to see here is that there's, ooh, nope. All right, Chris. Let's do this the right way. Actually, go full screen. All right, so maybe here. Whew, this light. Thought it was better. Let's get a little auxiliary lighting again. Yeah. So you see the blue jumpers there. Those are for switching between AC and DC coupling. And so I've got it on DC coupling right now. That's what we're going to use. And let's just hook up. So we're going to hook the ground probe to the bottom side, the bottom of this capacitor here. I'm going to hook the top side of the signal source, so it's just going to go into the R, and then we're going to monitor on the middle, between the junction, basically. So it's simple RC circuit here. Hopefully this will work. Otherwise I'll feel a little silly. It looks like it's not actually. There we go. Now it's over. Oh, okay. And then I've got the I've got this set to 50 ohm matched. So we'll see if that matters as well. Okay, so let's go back to the right screen. We still got all this stuff, and my autofocus is going a little crazy there. Let's see if we turn that off. Does that matter? That's exposure. How about there? Yeah. Okay. Hopefully that stops doing that now. And then this one should be in focus as well. Okay. Cool. All right. So what I'm going to do is, I'm just going to X out channel 1 actually. We can make this a little bit bigger. Or sorry, channel 2. And I'm just going to put a, let's just put a square wave out. So we're at 1 hertz. We're going to amplitude of 2 volts at an offset of 2 volts, so 0 to 4 volts. We don't need to do that. Let's just do 1 volt. 1 volt and an offset of 1 volt, so it'll go 0 to 2. So 0 to 2. Hopefully you can read that okay. And, sorry, I just looked at the chat. So, hi everyone in the chat. Glad you're here. Thanks for watching. 6 people. Okay, so let's turn it on, see what happens. So it looks like this is still pretty slow. Turn it on so it actually triggers. Looks like it's going to go now. No? Yes? Alright, so we're going to change the attenuation here. Oh, it looks like we can do 100x as well, so we could end up using the 100x probe here. Looks like noise. Alright, so let's do a little sanity check here, just to make sure. So just monitor the source. Make sure actually, yeah, we are outputting it. Looks like it. Okay. 500 millivolts per div. That's really slow. Let's just speed this up a little bit. We're at 1 hertz, so don't see any movement. Don't see any output. Let's try this. Still no output. Okay. You know, I did have, let's try it without the witches hats as well. I'm literally monitoring the same thing I'm sourcing, so it really should, this is my sanity check in action. Ooh, see some voltage now. That's nice. You're both set to DC coupling. This is, oh wait, one of these was, okay, so that's why. That was set to 1, sorry, this one was set to 1x, or 10x rather, it shouldn't have been. So, sorry, this one's not supposed to be set to 10x. So this is the source. Okay, let's drop. Okay, is this plugged all the way in? Yeah, that looks plugged all the way in. More sanity checking. All right. Time base will be expended. What does this even mean? Oh, okay. Hey, we got some signal. All right, so first off, let's just speed this thing up. This is ridiculous. Let's go up to kilohertz. Take this up to, so that would put us up here. We want to go at least 1 millisecond. We'll do that. And just zoom out here, and we can zoom out here. Okay. All right, so now, let's see, this is the scope now. So I want this one to be set to 10x. There we go. Okay, I think we're on track. Okay, there we go. Getting some signal. Looks good. Cool. Sanity has been achieved. All right, now let's try it with the witches hats, just to make sure these work. I do remember something acting wonky with these at one point. So that looks okay now. Okay. So now, let's go back to doing this thing. So we hook into here. I hook the source into here. We'll monitor the source. That still looks good. Okay, now let's go and do this. Now we should see some kind of RC behavior here. It looks like we are, but not what we expected. Looks like the it's not quite, so it's definitely slowing down the edge here, right? And that's kind of what I'd expect to see. However, whoa, Adafruit showed up. Hey guys. So yeah, not what you'd expect to see. Well, I actually don't know what we expect to see. I mean, let's see, there's a 1 kilohertz sine wave. So we've got a 1K and a 0.1 microfarad. You multiply those together, you got a RC constant of what, 10? 100? Oof, 10, yeah. 0.1, so it's 0.0001 times 100, so 0.001. Ooh, okay. Anyways, let's see if this gets more extreme here. If we change to a higher frequency, right? So we should see the edges start to change a little bit more. Now, if we go up even higher, so what we're seeing is basically the impulse behavior going through the RC circuit, right? So now we start to see the edges really getting taken off here. Right, so we have a ramp. So as this, well, let's see if we can't view this a little bit better here. Why is this not zooming in? We want this to be more like that, more like, there we go. Oh, you can scroll. Okay, so in the source, you have to actually scroll in the settings menu, but then you can kind of make it look how you want there. Cool. So if we change this again, obviously, if we keep going up, we'll keep seeing less and less. You'll see more shark fin type behavior here, right? So this is basically showing the relationship of, you know, a filter, a low pass filter. That's what this is. Basically, all the high frequency components, which is, you know, the squareness of the square wave, that starts to get removed here, right? If you did this long enough, you start to lose amplitude as well, right? You lose amplitude on the signal here, but you would also start to get down to fewer and fewer components, right? So how to say that better? I guess it's more about the sharpness of the filter. So right now this is a nice smooth filter, and that's actually what I wanted to do here too. So I need to kind of play around a little bit here. But what I'll show you is that there's other stuff that we can pull in here from Waveforms, which is the software we're using here. And this is part of the Analog Discovery 2. This is what controls it. So what I wanted to do, though, is let's look at the spectrum here, right? So we might need a second probe, and I will be figuring out some of this stuff. All right, so we got channel 1, channel 2. Let's see. We're going to turn off channel 2. And let's see if we just hit run, what happens. Yeah. Okay, excellent. So this is showing the spectrum of channel 1. Aha, this is actually the... Okay, so let me change this around a little bit here. So what we should see, this is actually... All right, let me tell you a little story here, actually. Because this is actually kind of important to contextual electronics. So, okay, how did contextual electronics start? My big story. Why did I start this program in the first place? So I went to school for electrical engineering, and my junior year I took a signals and system course, which I loved. I really, really loved it. I had a great teacher, really liked him, Mike Branicki, really, really good guy. And so even though it was a course that I liked and everything was great about it, we started doing Fourier transforms, which I'll get back to in a second. But Fourier transforms are this very difficult math operation that basically you need to do a bunch of math. You need to understand the underlying stuff for it to make sense and really to get through it. Right? This is a class that really weeded a lot of people out, and almost me as well, even though I liked it. And I'm talking like 30, 40-hour homeworks and just the whole shebang. Anyways, 3 or 4 weeks in, we were still doing the same homework, and we were still struggling with it. And then finally, at one point, even though they said this, at one point it finally clicked, and we said, and I basically figured out, I was like, oh my God, it's important because a Fourier transform lets you see the frequency components. Now, they said that the first day, right? They said that the first day, yes, this goes between the frequency domain and the time domain. And you can say it, and that's different, though, than showing it. What they should have showed, and this is me getting back to my story here now, what they should have showed is this. This is exactly what they should have shown. And what they really should have shown, let me try and squeeze this up a little bit here. What they really should have shown is this, is if we go, all right, let's take this back down to 100 kilohertz now. All right, now let's take it down to 50 kilohertz. Okay, cool. Now let's take it down to 20 kilohertz. Right, let's zoom in here now. Right. Oh, you can click and drag too. That's nice. Oh, look at that. You can slide it, and then you click and drag, and it actually expands it out. Okay, and then let's go down to 10 kilohertz. This got frozen. What happened here? Oh, you can only do one or the other. Okay, well, that's good to know. So what I'm trying to say, though, is basically this exact thing is what they should have shown us. Because this is showing frequency content of signals, right? And I know, like, it was on me, I didn't quite get it, and this was part of the learning process, but that singular experience is what I point to as the reason behind contextual electronics. And yeah, basically because there was no context, right? That's what I'm trying to get at, right? That's where the name comes from, is that there was no context. I didn't know why I should fight for 3 weeks of doing math, and this is the answer, right? Because basically what I'm showing here is that you don't use the Fourier transform math, like that's very theoretical and optimal. Like, that's not the right word. What's the right word? It's there's a better word for it. You usually use approximations when you're doing stuff like this. You use DFTs, right, instead of FFTs. So, well, even if you're doing fast Fourier transforms, usually for digital stuff, using discrete Fourier transforms. Anyways, the main thing that we should have seen is we should have looked at a spectrum, right? Someone should have brought in a spectrum analyzer and shown us a sine wave tone. I can show you right here. All right, let's do this. This is what they should have shown us, right? And this is why I'm actually really excited about the this tool. What I'm gonna do is actually switch. Oh, still getting better at switching over. Sorry about that. Okay, so what I'm gonna do is I'm gonna monitor just the output from the signal, right? So now I'm just monitoring the output from the signal generator, right? So the input and the output are the same. And like I said, if we see this, we'll actually see the frequency content here, right? And like I said, but if we switch this over to sine wave now, oh, look at that, single tone, right? This is why this is important, right? And now you see the single tone, and you can move it up, and you can move it up, and you can move it up, and you see this is going between the time. The top is the time domain, the bottom is the frequency domain. And my God, this is what they should have done that first day. And I'm a little disappointed that they didn't. And this, well, I guess this got me into the education racket. So there's always that. Anyways, going back to the comments, let's see. Kenneth says 0.1 microfarad and 1 kilo ohm. Yeah, it might have been wrong, Kenneth. I don't know what the values were. I should have checked better. The point is, it doesn't matter here. I mean, it does matter, but it doesn't really matter. Let's see. Who else is talking here? Adafruit says they're everywhere. That's creepy, guys. But thank you for everyone for showing up. Yes, the software is Waveforms 2015, which even though it's 2017, halfway to dozens. Yes, Kenneth also says the 50 ohm load shouldn't matter. Yes, that was not the problem. So. Okay, great. Cool. So what else do I want to show here? So this is definitely something that I'm excited about. Just having the frequency content here is really nice. I mean, obviously you need multiple channels. What we can do now is same thing, right? So now let's take a look. We're going to remonitor. Now we're monitoring. Can you see that? Yeah, you can see that. So we're monitoring at the middle of that RC now, right? So now what we can do is, let's see. So if we take this back down, so now it's at 2 megahertz. Let's go back down to, 10 kilohertz, right? And so this is all zoomed in. Oh, you can scroll on the x-axis too. Oh, isn't that nice? Okay, that's actually great. So, cool. and then you can click and drag. All right, so I'm still learning a lot of this stuff too. So it's between 0 and 2 volts. Okay, so I lost this thing though. I'm going the wrong way. Okay, I gotta zoom in over here. Just trying to find my. Whew, where is this thing? Did I lose it? Aha. I might have lost. Just double check. Okay, let's do that. I'm trying to figure out how to reset this thing. It looks like that's the signal there. I think it's this little guy down in the noise. And actually we can just check if we turn on the scope again. Right, we can actually just sample. Okay, something's wrong. What is wrong? Oh, there it is. Okay, so the signal's there. That's good. It was there. What is going on here? Okay. Am I just losing the connection here or something? Okay, so it's there. You can see, I mean, it's kind of hard to see probably for you, but I can see that it is sampling and moving and stuff like that too, so. Oh, wow. I'm going to get really spoiled by this now. So there's a 0 point. And then this is, the right side's the trigger, right? So you can see that it actually is triggering. If you move the trigger off, it'll start flowing probably. Yeah, there it goes. Okay, so it is actually coming in now. All right, so let's turn the spectrum analyzer back on. Okay, aha. Okay, there's our signal now. Let's zoom out on this guy. What was I even trying to show here now? Aha, yes, what I wanted to show is the filter behavior, right? So what happens with a filter is basically as you move higher and higher frequency, right? A filter, how can I do this? All right, so I'm going to, let me just, excuse me for 1 second here. So I think if I do this, and then I do this, and then I do this, let's see if this works. Sorry, just trying to load up my programs here. Smooth draw. Can you post? Paste. Okay, cool. Yes, so now what I can do, I'll show you on here. Middle screen. So what a filter really looks like is like, so in the frequency domain, it looks like this. Right? Well, at least an RC filter, like what we're doing here, right? So an RC is, we've got this, and then there's a C, and then we're treating it like your ground, and then there's an output, and right, we're input here, and I apologize for my terrible writing, output here, right? And so an RC filter looks like this. So what happens now as this spectrum, as this sine wave moves to the right? Well, let's just go and see, right? We can just go and do that. What I think is going to happen is, I don't know if this is drawn to scale here, but what happens is so say we're out here now, right? So now the sine wave moves out here, right? What the filter is doing is basically it's going to chop off the top here. That's basically what it does. And so we can try and see that in action. Okay, let's see if that happens. So I'm just going to go and up the frequency. Oh man, that's even cooler now. I'm just mouse scrolling. Oh, well, that's a little bit further out than I thought it would be. Okay, so what we're really seeing, to go back to here, what we're really seeing is closer to this. It's just a really gradual, right? Because we're not actually losing much amplitude here. It doesn't look like, at least, unless it's, I don't think it's, yeah, I don't think that it's actually readjusting. I don't think it's auto scaling. That would be bad. Sample, yeah. And there's different sample types, stuff like that. Peak hold, minimum hold, continuous, all that stuff. It's for 10 megahertz. That does not seem right. That's frozen. We're not actually running that now. Okay, so let me stop that, run this. I'm a little discombobulated here. Looks like we're actually running. Okay, I'm going to zoom in. There we go. Okay. Okay, so something's weird here. It's showing 10 megahertz up here. I wonder if we're aliasing. Yeah. Okay, that looks kind of accurate now. Okay. Okay, so at least we see it moving. And it's kind of... Okay, it looks like it's rescaling itself. Let me move this out even further. Okay, so now we've got a 0 to... Let's maybe go to 5 megahertz if we can. Not sure it'll go for that. I can't go for that. No, no can do. Yeah, and this definitely feeds into oh crap, I'm sorry. Yep, still learning. Still learning. Sorry. Switch screens, yes. I feel like someone needs to, I need to have like a bell. So here's an idea. Here's an idea for all you IoT folks. I need like a bell so that you can just like send it a tweet and then it rings a bell here. Chris is stupid. Let's see. So what do people say? You might be off by a few decades from the knee on your Bodhi plot. I agree. I think your cap is 1 to the 10s of picofarad. Yeah, I think you're right. I might have just read that wrong on my... let's see. Yeah, it says 102. That's 100 puff. That's 100 puff. So I think I measured it as well, and I was measuring it wrong, I guess, huh? Anywho, so yeah, it looks like 100 puff on that thing. Yeah, so actually, let's actually get a better... let's see. I can... So thank you, Kenneth, and people that noticed that. This is a 4.7 microfarad. That's probably a little bit better, huh? Probably a little bit overdoing it, but let's see, 4.7 microfarads. Yeah, that should be okay, right? So let's see, 1 microfarad at 1 microfarad at 10K would be 0.1 cutoff. Yeah, this is gonna be too big. What else we got here? We've got 221. Where's my cap kit? I just bought a crap load of caps too. Question is where I put them. See, my big thing is I don't usually have a lot of through-hole components around because I'm not building stuff with through-hole that often. Where the hell did I put these things? I know I just saw them. Buttons. Logic. Oh. Nope. Still a little messy in here. Chicago-based magazine. Aha! Oh, yeah, yes! Found it. Still there? Everybody still there? How about this beast? Jesus, what a mess. Oh no, this is all Picofarad stuff too. Crap, 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 crap. Well, what do I have in the box of goodies here? If I have any smaller capacitors. It's another 10 microfarad. Oh, it's 47 microfarad. That's even worse. 310. I have no idea where my parts are. Well, I guess we're just going to slow all these signals way the hell down. So, that's the 47. Where'd that 10 go? I guess we'll see a lot of decade stuff happening here. Okay, so see, that's weird. I just realized that I wasn't even. I'm just monitoring the source still. So yeah. Yeah, so I've just been monitoring the source. So I'm just wondering if this thing's sampling is kind of weird. So it gets out to 10 megahertz. It looks like it just folds back on itself. It must be aliasing. So yeah, it only goes to 10. Okay, so if we look on the center point here, it's not going to handle 10 megahertz real well. Oh, come on. Seriously? Oh, yeah. Gotta hook up the grounds probably. Yeah. There it goes. This has been properly filtered now. Okay, so the filter went away. Jeff asked, does the 82 have both 50 ohm and high impedance? No, it has 50 ohm and no and 0. That's the two options. So, I guess low impedance. Unless 0 ohm or 0 is referring to something else. So, it's just a direct. That's really what that is. Anywho, okay, so what are we doing here now? So let's slow this mofo way down. And then let's make sure we're actually zoomed in where we need to be. Okay, so now we're at 100 kilohertz. Let's see if we can actually see the signal. Once again, appears to be missing. Okay, let's try this guy again. Turning off channel 2. I wonder what's going on with this. This is kind of weird, huh? Alright, there it is. So these might just be shoddy witches' hats. So there's our signal. So this is the source signal. This is the so just kind of touching between the two. I do expect this to be filtered, so that's okay. And I guess we are seeing an offset here too, so it's not like it's not seeing anything, right? And just the slightest amount. So anyways, let's keep zooming in on this thing. We'll take this down a little bit more. Oh, this isn't running. You can just barely see it now. I think that's it. Yeah. Okay, there we go. Yeah, this is about the filter I'd expect now. Okay, so it's going to go a little bit slower, but we do see the amplitude now. And again, if we want to see the, no, it's not showing much here. That's weird. There it goes. Oh, it's just not, it's not set at the right, I'll slow this guy down. There we go. Okay. So now, like I said, so we should see the amplitude change as well. You are seeing the amplitude change as we go slower to faster, right? So it's a low-pass filter. A low-frequency signal is going to allow more of the signal through, right? And as you move up in frequency now, so remember, this isn't running. So as you move up in frequency, we're really just watching this guy over here. As we move up in frequency, oops, I changed the amplitude by accident as well. So as you move up in frequency, the signal, going the wrong way, the overall, let's see, how can I do this? I can zoom out. There we go. Okay. Unfortunately, we're at 1 hertz, so it's going to start to, it takes a little bit longer. So 2 hertz, looks like we're about there. Remember, this is a really low pass filter right now, so like the time constant's really low because it's a it's a 10 microfarad and a 1K or 10K resistor, so pretty low. But as we start to up our frequency, we'll see the amplitude here. I don't know if can I do markers? Ruler. Oh, there we go. Wait. How do I do vertical markers? Nope. Oh, that's kind of nice. Measure free. Ooh, look at that. Anywho, and then I want to change. I just really want the marker to stay the same, so we can see as we go higher in frequency, we see that initial level there, it really starts to drop. It's just taking a little bit of time because it's just such a slow time base. So now as we're up at 50 hertz, 100 hertz, whatever, all these are getting filtered pretty significantly, right? So now if we turn on the spectrum analyzer again, right? So now as we, let's turn this back down to a, lower frequency. So 20 hertz is up at minus 27 dBV, right? So what we expect to see now is as the frequency moves out to the right, we should see the amplitude of that frequency signal start going down. So that's now minus 36, minus 40, minus 45. So unfortunately, the frequency moves up in kind of log scale almost. But now we see already we're out here, we're at the 2 kilohertz mark, and we're half of what we were before, right? Same thing if we keep going out. Oh, I folded over. So you can see we're outside of the, so this is a sampling problem. I'm surprised that it does this actually. I mean, I'm not surprised that it does it. This is a, this is a sampling issue. And maybe I should just put a anti-aliasing filter on here or something, but that is interesting that it doesn't call it out. I guess maybe there's no way to tell. So if I resample now out to 5 kilohertz, it should show up out there. Yeah, you see that. So it is kind of problematic if we yeah. So basically it's following this trend here, and I think there's a whole separate tool for doing Bode plots. Spectrum. Oh yeah, here we go. But I'm not doing that today. So basically, you know, a network analyzer, you could start to do plots basically in this same way, right? So if you wanted to do a sweep, you could start to view the filter characteristics, because it's going to sweep through from, you know, 1 hertz to 100 kilohertz, and it's going to track the behavior and basically just do what we just did manually, right? With the spectrum analyzer, it's just going to show the peaks and then plot the peaks, right? Each peak would be a data point, and then what you do is you kind of connect the data points, and that shows the behavior of the signal. And the more you sweep through these signals, if you sweep in an analog way, you can get lots of data points there. It takes a while, but you know, lots of data points. Okay, well, I think I only had like 2 or 3 screen incidents. I'm getting a little bit better. I also was spending a lot of time here, so yeah, hope that was okay. You know, it's interesting to see what you can do just with an RC circuit, and just really it's more about talking about the test equipment than it is about the circuit itself, right? The filter's kind of, well, obviously the filter did matter in this case. Had the wrong capacitor in there. Thanks to everybody who pointed that out. Thanks to everybody who watched. That's nice. I definitely appreciate when people do that kind of stuff and jump in and say hello. So that's hopefully will be more in the future. This is my 4th night, 5th night, 4th night. I think fourth night of streaming in a row. I'm hoping to make it a week, and so I hope you'll join me in future. It might actually not always be in the night. I did it yesterday morning, so it's just kind of whenever. But if you subscribe to the channel, you should also get notifications. I will, of course, once again call out, we do have a forum for Contextual Electronics. It's a free, open forum. You can request if you got stuff you'd like to see, or even just stuff about the Analog Discovery 2 you'd like to see. Really just playing around with this and trying it out. So, would love to hear from you over in the forum, and check out what we've already got over there. So, that's all for now. Let me just double check there is no... no, looks like there's no real comments there. I mean, there's comments, and thanks for the comments. But we'll see you next time. Thanks for watching.